So, good morning, everyone. This talk is called Rust is not about memory safety, and it will try to explore how perhaps memory safety is not the most important thing after all, and perhaps there is something different and larger than that. This was inspired by this blog post. I even stole the title from that. It's a good read, and it's worth a look. I'll show the link again at the end. So, 2 words about me. I've been doing software engineering for about 30 years. Most of that has been C++. For the last few years, I've been using Rust as well, also for production. I've spent the last 12 years at a company called Thales, Norway. We deal mostly in secure communications of various forms. And we are hiring. This link will show you what's open right now. It changes, so if you don't find your favorite job there today, maybe tomorrow. Well, there is something about Rust, something that makes people get very enthusiastic. And I stumbled over a joke about this a while back that I thought was a bit appropriate. How can you tell that a developer uses Rust? It's easy. He will tell you, whether you want to hear it or not. And there is some truth to that. And why is it like that? And by the way, I'm using he. I'm not gender neutral here. I think women are a bit more polite than that. It's usually men who does this. This level of enthusiasm can be a bit too much. It can alienate people, drive them away. So why does it become like this? I don't think that is about memory safety. Memory safety doesn't generate that kind of enthusiasm. It's just a practical engineering thing. So where does it come from? Well, is it because it's a new and cool language? Nah. There are many of those, and they don't all cause this. There must be something more. I've noted down some random quotes that I found here and there. And I kind of like this first one. Rust makes it hard to express programs that are wrong. And that will come up again in a few places during the talk. You may have heard about fearless concurrency, but I like this one as well. Fearless refactoring. If it compiles, then it usually works. Think about that for a second. That's unusual, isn't it? When did you get that feeling in a different language? So if you get that feeling, then that's something special. And then some people go as far as this. I think that's over the top. We're not going to go there today. What we need to talk about is type systems. I think it all starts there. You probably all know about the difference between dynamic and static type systems. We will also look briefly at strong versus weak type systems. That's a bit more fussy, but we'll give it a try. For dynamic versus static, a static type system is a type system where the value in your program is bound to a type at compile time. So the compiler knows exactly what this type is and what operations it will support. While in a dynamic type system, the value is bound to type at runtime. So only when you run the program can you find out what operations it will support and if the program will work or not. And you can try to categorize languages and put them along an axis. And I just threw them on there. And one important thing for me is that in a static type system, you detect more bugs at compile time. And you want to detect bugs early because that's the cheapest way to find them. Compile time is much more economical than having to test your program and run it. And then there is one thing that struck me only recently, that I had never thought about before. It's not as clear-cut as this, always. What about the null value? Many languages have pointers. Some call them references. C++, C, Java, C#, and so on. And any such pointer can be null. We are all used to that, but think about it for a second. Null does not support the same operations as the type you wanted. It doesn't support any operations at all, almost. So it acts like a different type. De facto, it is a different type. So any pointer is actually one of two types. It's the intended type or no. And when you think back to the definition of a dynamic type system, well, that's what it is, because it's determined at runtime. So these type systems are not fully static. We think they are, and the compilers type system think they are, but in practical terms, and also in type theory, they're not. Rust has enums with data, so it's some type, and it could look like this. We have an enum called foo. It's got two variants, variant 1, variant 2, and if you have variant 1, it has associated data with it. It has 2 as a tuple. It's an unsigned 64-bit int and a 64-bit float. And if it turns out to be variant 2, it has 2 named fields. One is a 32-bit float, and the other one, bar, is a string. And this allows for new ways of coding, new ways of designing things. For those of you who listened to Klaus's excellent talk yesterday, he showed an example, a classic example from school books about oriented design, the shape and the squares and the circle, and so on. And you can represent this with an enum. It has 2 variants, it's a square or a circle, and then you have the attributes of each variant. To the right, the square has 2 points to define the corners, and the circle has a center and a radius. And to operate on this, you typically use pattern matching. So here's the draw function. This is much more simple and naive than Klaus's example. But you have a draw function. It takes a shape, draws it on a canvas, and so to do that, you need to match on it. And if it's a square, we actually extract the data of the square. We map them to the lower left and upper right name, and then we can use those names to implement the code that we need. And the same with the circle. If it's a circle, we extract the center and the radius, and we can use that to implement the function. Nice and simple. This can sometimes be a very good alternative to using class hierarchies. There is radically less boilerplate involved, and you can use it instead of inheritance in many cases. If you use it in the right place, your code will be simpler. Klaus had some really good guidance on when to use this. If you are more likely to add new methods to your code, then some types can be a really good option. If you're more likely to add new variants, then maybe a class hierarchy is better. And yeah, this comes with new and good patterns for flow control as well. In addition to the match statement, you have an if-let statement that lets you check what it is, and if it is what you are looking for, you can use it. Notice that the only way you can get at the data inside the enum variant is by pattern matching. There is no way you can use a circle as a square or vice versa. So this is safe. You can't misuse this. So the only way to get to the inner value is through matching. And if you do a match statement, then all the variants must be handled. And I put that in quotes because there is a loophole, but it's frowned upon. You're not supposed to use it. So this contributes to making it hard to express programs that are wrong. Well, what about C++ variant? It's not bad. I don't find it very ergonomic. I think the code sometimes looks a bit messy. It has some restrictions. It has only one value per variant. Actually, the type is the variant, which is a bit restrictive. It has also no real pattern matching. And there is quite a lot of UB in the API. You can absolutely use something as something that it is not. But if you're using C++, please use it. It's very useful. I just wish it was better. Kind of a lost opportunity. Okay, so that's it for some types for now. But it connects with the next theme, which is error handling. sort of a simplified view of the evolution of error handling. Error codes from C and so on, and then exceptions were introduced. And then some languages have introduced some types for error handling. Rust stole this from Haskell, I believe, and maybe others. In the C days, we used to do it something like this. You have a function, foo in this case, and it does something, and then it calls bar, and bar can fail. And then you check the return value from bar, and in this case, if it's different from 0, then you have to clean up everything. You have to free your resources, free memory, and so on, correctly, hopefully. And then you bail out. And there can be many blocks like this. And they are all different, and they all have to work perfectly, and you need to do testing and so on, and it can get very difficult. So to help make this easier, we now have exceptions, which moves the cleanup code to finally blocks or catch blocks, what have you, depends on the language. And there are nice language features and patterns to ease the cleanup. Destructors and RAII in C++, idisposable in C# and so on. But there are some pitfalls with exceptions. It's not all rosy. I've tried to make an example here. We have a foo class. It has a bar function, and it does some preparation, then it calls do, and then it calls final. And do is over on the right. Do is a private function. It has a couple of steps. Looks okay, right? Foo has invariance. So there are some states for its members that are legal and some that are not. And the invariance basically says that you cannot be in an illegal state. You have things about the object that needs to be true in order to call its member functions, so invariance. And in this case, the first function breaks the invariance, then do does the main work, and then you fix it afterwards. Now, what happens if someone comes along and changes this code to throw an exception? Well, if you throw the exception, you unwind the stack and you skip the fix invariance part. So you have now left your object in an invalid state. And my problem with this is that you get no help in finding this from the tooling. The compiler does not detect this. It doesn't help you do this. So when you change do, you have to go and find each and every function that is called, that calls do, and check if you need to fix something. We don't do that normally. We just get caught out by this bug at some point. And not only do you have to check every function that calls do, you may have to check every function that calls every function that calls do. It propagates up. And I've seen guidance sometimes that you should never use exceptions for flow control, and probably because of things like this. But isn't that ironic? Error handling is okay, but flow control is not. Well, error handling is flow control. It's difficult flow control, and it's flow control that you do not test properly sometimes. So it would seem it would be worse to use exceptions for error handling than for flow control. I'm not trying to bash C++ here. This could be any of the other languages, really. And the problem here is that the errors are no longer part of the type of the function, its signature. So the type system cannot help you. Fixes were made for this, or attempted in some languages. You can have the functions declare the exceptions that they may throw. It would fix this one, but what happens if you put an annotation on the do function is that you have to put an annotation on the foo function as well, and then you may have to put the annotation on functions that call foo, and so on. So it has cascade effects that propagate up, and that meant that maintenance became hard and difficult and frustrating. So this was failed. This was abandoned. The attempt to fix this failed because of these cascade effects. What you can do instead is use sum types as the return value. So what Rust does is that it has this result with an OK or an error. If the function fails, you return OK with a value. And then if it succeeds, you return OK with the value. And if it fails, you use error. Nothing radical here. C++ even has the same thing. This makes error part of the signature. The type of the error is part of the signature. So now you can do the same thing, and when you change the code on the right to return a result type, then the compiler finds the problem for you. And of course, this is the reason, I guess, why the same type was introduced in C++. So you can do the same there now, which is really good. And once you've done this in Rust for a bit, you tend to want to do the same thing in C++ all the time. So Rust makes it hard to express programs that are wrong. You get help from the tooling to fix these kinds of problems. But what about the cascade problem? That was annoying, right? And now we're back to that again. They kind of fixed this with the question mark operator. I'm not sure if you've seen that, but this is some syntactic sugar that helps you write more compact and readable code. Here's a simple example where we have a function that returns a result. Well, that's not important, actually, but the important point is the question mark operator on line 2. So it calls a function called bar. That returns a result. And then there's a question mark after it. And what the question mark does is that if the result is OK, it unwraps the result and returns the value inside the OK variance. So that gets assigned to V. But if there's an error, it returns the error directly from the function, so it bails out. So this is actually syntactic sugar for this. And you want to write the stuff on the left, right? Not the stuff on the right. So it matches on the result. If it's OK, then you get the inner value. If it's an error, it returns that and bails out. So quite readable. And you can pepper your function with this. You can have multiple question marks in there, of course. And you can use this to write more advanced stuff. I'll give you 2 seconds to look at this. This function tries to decode fields from an IPv4 header. And the data comes from the packet, and the packet is of type bytes. Bytes is a type that comes from a crate called bytes. And bytes is a crate that implements advanced buffer handling for network I/O. It does some magical things to sort of stitch buffers together and so on, so that you can just use this at an abstract level. You don't need to really care about packets and chunking and stuff. And this returns a result, and the result, if things succeed, is a struct called IPv4 header that has some fields. You can see how we try to populate that below. And if it fails, it returns the try get error from the bytes crate. And the IPv4 header is constructed here. And the different fields are populated by calling packet try get functions. And these functions will get you a field, a value, if there is one. If there is no more data in the packet, then they return an error. So version is populated from the first byte of the packet, if there is one. And if the packet is empty, you bail out. And the second field is then populated from the second byte of the packet, if there is one. And so on. And notice how I don't have to write any kind of tests here for buffer length or anything like that. There are no ifs here. It's all handled by the question mark operator. And there is also one more wonderful thing, and that is if I forget the question mark for the version line, for example, then, well, try get returns a result. But version is a byte, so it's not type compatible. So if I omit the question mark, it doesn't compile. And the end result of this is that you hardly have to write any unit tests for this, because most of the things that can go wrong fail at compile time. But that doesn't solve the cascade problem. The result can only hold one type of error value. It's a single value. And you typically want error types to be specific to the API you are implementing or to the level you are at in your architecture. Which means that if you propagate errors up through your architecture, they need to be converted. Errors need to be converted as they propagate up. And in this case, we returned the byte error type. And that's not really appropriate for this function. So we want to return something else. We want to return our type of error. And how does this compile? What if one of these functions, one of these question operators, detect a failure? Well, there is some provision in the language for that. There is a standard trait in the language, in the standard library, called from. A trait is sort of like a cross between concepts and abstract classes. And from is used for conversion. You can implement from to define conversion from one type to another. And this is a from conversion from try-get error to the protocol error that we saw. And what happens now is that when you call the question mark operator, and the compiler sees that it would like to convert from one error type to another, it will use the from implementation if it exists. So it's a specific conversion for a specific case. It's not a blanket implicit conversion as say, C++ has, where conversion happens whenever the compiler finds it useful. This is for that specific case only. And that solves the cascade problem. So the conversion here is automatic. So your code is still clean. So to summarize, the error is now part of the function type. So it solves many of the maintenance and refactoring issues. It finds errors at compile time. You get ergonomic propagation of errors and handling of conversion. And missing error handling does not compile. If you get a result that you don't handle, the compiler complains. And this means that anywhere in your code, if you decide to return an error value, you are confident that it will always be handled. All errors will be handled eventually. There is no error that can propagate up your stack and terminate your process. So this makes it hard to express programs that are wrong. There are similar things with option values. Here we have some old school code. I've written lots of code before the optional class was standardized. And you tended to end up with some special values that meant no value. So in this example, we have a function called bar, and that usually returns an int, but sometimes it cannot get you the int you want, and it returns a special value, which means nothing. And then you handle that case. Otherwise, you do what you came to do. So on the right, you have the function that produces this. If it fails for some reason, it returns no value. Otherwise, it returns the stuff you wanted. And at some point, you will probably want to refactor this to use optional. So you return null opt instead. And what happens now on the left? In maintenance, maybe you didn't even know foo existed. You just changed bar. Maybe you have 100 places where you call bar. Well, you won't get to handle no value anymore. And you don't know because you don't know foo exists. The problem is that C++ is perfectly happy to compare an optional int with an int. And if the int is no value and the optional is null opt, well, they're different. But it builds, which I think is bad. Implicit conversions can be harmful. Most of them kind of are. This was invented long ago and with the best of intentions, but I think maybe they do more harm than good, because they prevent the compiler from detecting bugs. And it contributes to giving C++ a weakish type system. If you do this with a stronger type system, then the results are different. If I change the code on the right to use option, I return none if it fails, and then some if I get a value. So these are the variants for the option type. Now over on the right, the compilation fails. because Rust will refuse to compare an option of int with an int because they're not the same type. You have no business doing that. So now every place where my refactoring on the right affects code, I get a compile error, which is nice, because I won't find the fault in production. I have to do pattern matching instead. So I have to go and fix all the places where my code needs fixing. So the lack of implicit conversions results in less bugs. Rust makes it hard to express programs that are wrong. And I think stud optional is also dynamic typing. You can't dereference an optional before you know it contains a value. You need to find out at runtime. This is not fully static. Like with pointers. Stud optional is kind of dynamic typing as well. Nullup does not permit the same operations as an actual value. The actual value is bound at runtime. Actual type is bound at runtime. So it's kind of dynamically typed. You have to check, does it have a value? And then you can use it. You could say that the Rust code is somewhat equivalent, but you can't get it wrong. The compiler leaves you only with one way to do it, and that is the correct way. You can't fail at runtime. It's hard to express programs that are wrong. And it's similar cases with Struct initialization, in a way. Here I have a Rust struct. It's got 2 members. And I want to initialize it. And I just initialize 1. My mistake. Compiler complains. Will not have this. You have forgotten to initialize B. I think this is what I expect. C++ has a lot of history. Yeah, I have to put in B and everything is fine. C++ has more history. This is the recommended way to do it in C++. C++ core guidelines C48 requires me to put the curly brackets there for reasons we will not get into here. I can default initialize foo, which is fine, useful. I can also do this. I'm not a fan of that one. I can omit B. Because what happens if I now come along later and put a C in? Well, on the left, it fails to compile. You forgot to initialize C. So the compiler will tell me every place I need to go and update. And I can fix that, and there is no bug in production. But on the right, well, it still builds. So I'm not a fan of that. But Rust makes it hard to express programs that are wrong. This will be known territory, I guess, but the life cycle of a variable, what does assignment mean? If it's Java, C#, and it's a class, it means that the object is shared. You have reference semantics. You copy the reference from B to A. And when the references are gone, you get garbage collection. Changing B changes A. I think that's difficult sometimes for me to grasp. It's easy to forget. But that's the way reference semantics works. If this was a C# struct, then the object is not shared, it's copied. So changing B does not change A. So that's value semantics. C++, little bit more complicated maybe. You copy the value based on the type. So if it's a value type, you copy it. If it's a reference type, you copy the reference. So you get reference semantics or value semantics depending on the type and how the type is implemented, which has some challenges. You have the same syntax at the point of use, and you can get some confusion here and loss of performance. I think this is maybe part of the reason that C++ was said to be less performant than C back in the old times. because people would write code that would, perhaps unknown to them even, make a lot of copies, unnecessary copies of strings and indexes. But we got move semantics. So cool. New syntax to move stuff. The object is moved instead of copied. But the moved from object can still be used. Why? Its state is valid but undefined. What does that even mean? It doesn't mean undefined behavior. It just means that if you call a function, it's not allowed to have undefined behavior, but it must do something valid, whatever it wants, actually. Which can be hard to relate to. You shouldn't do this, of course, but you can, and you will. And objects of the same type can even have different behavior. If you have a string type, which uses small string optimization, and you move from it, the implementer of the string class is perfectly free to let the string keep its value if it's short and become empty if it's long. So this is odd. And there are also parts of move semantics that makes user-defined types complicated to get right, because you now have 5 special member functions. And of course, when it comes to the fact that you can still use a moved from object, my biggest gripe with that is that it makes it possible to introduce bugs. You shouldn't be allowed to do that. The compiler does not catch this for you. Well, I guess there are warnings now in modern compilers, but I haven't seen much of that myself yet. Anja, does anyone know if you can turn on warnings for this today? Clung tidy, yeah, right. Okay, so not in compiler itself, but static analysis. Yeah, makes sense. And special member functions, fun. This is a simple buffer class. Put some data on the stack, and that's the size. And then all this has to be correct. I used the copy and swap idiom just to make this simpler. This can be hard. We won't spend time on that. In Rust, it's move semantics by default. You move the object. The old object no longer exists. So if you use it, you get slapped on the wrist. The compiler refuses you to access the old object. And the destructor is not called. So if I assign B to A, then the destructor is not called on B. The responsibility for destruction has moved to A. And this is nice. You get a compiler error if you do it wrong, but it's also nice in the sense that because you move the responsibility for destruction, the move is just a mem copy. You just copy the footprint of the object because it's harmless. It's all you have to do because A now is responsible for destruction. You can get value semantics if you implement a trait called copy. And you don't have to do it yourself, you just ask the compiler to do it, and it generates the code for you. So there are no special member functions. All those bugs are gone. And if you try to access the object after move, you refuse to do that. The compiler will flag it as an error. So Rust makes it hard to express programs that are wrong. Next topic, member functions that consume their arguments. Or methods that consume their arguments. It's not restricted to member functions. This is a regular function, and it takes B as a value. When you call foo, the value you use as an argument to foo gets moved into the function, just as you move with assignment. So calling foo consumes the B argument. B can no longer be used, which sounds inconvenient, but it has some really nice practical applications. You can still copy B, but you just have to be explicit about it. Which is also nice because it means all the copies you generate in your code are visible. There is no implicit copy. If you want to copy B, you have to explicitly specify that this is what you want to do. But you can also use this for member functions. So here's an example of that on the right. You have a struct B, And a struct and a class are the same thing. Rust does not have class, it's just struct everything. And you have an implementation block where we implement the member function for B, and the member function takes self by value. Self is the object itself. It's a shorthand. You don't have to specify the type because it's given. And this is now by value. So when I call b.foo at the bottom, I consume B. The object no longer exists. I cannot do anything with B after that point. So what if this was a file? Close takes self by value. Write doesn't. But close takes self by value. So if I call close, and then I try to call write, boom. Not allowed. F is gone. It was consumed by close. And this is cool because it means the compiler checks that I use the API correctly. If I use the API incorrectly, it gets detected at compile time instead of a runtime bug. And you can generalize this into what they call the Typestate pattern. So your model states as type. You can only call operations permitted by the state. And this is enforced at compile time by the type system. Here's a simple example. This sort of models what could be a network connection. So you start out with nothing, then you call connect, and you get back the connected state. And I've omitted error handling here, just to keep things simple. You get back the connected state. The connected state allows you to authenticate or close. And when you authenticate, you change state again to authenticate it. And that consumes the old state, so you can no longer use the old state. You have switched to the new state, and the old state is gone. If you close, and there's nothing left. And in authenticated, you can communicate. And communicate does not take self by value. It takes it as a mutable reference. You can change the object. But close consumes the object. So then the connection is gone again. So you get an API with a usage that is checked at compile time. You cannot do anything illegal. You don't have to check in your member functions, am I in the correct state? Is the user of the API allowed to do this? It's checked at compile time. So kind of cool. It makes it hard to express programs that are wrong. And when you sum this up, all this has practical implications. Static type systems catch errors at compile time. Dynamic type systems require more testing because you will have ifs and buts in your code to test things before you use them. And those ifs and buts require testing for coverage. This detection of errors at compile time means that Rust code is more likely to work if it compiles. And you get a feeling for this when you do refactoring. Things are less likely to break because Rust catches more stuff at compile time when you refactor. So you typically end up with breaking less stuff. And one of the reasons for this is that when you do refactoring, you usually have to make note of a lot of loose ends. I changed this, so I have to go back and fix this and this and this, but I can only focus on one thing at a time, and then you have to make note of all the stuff you have to do later that you must not forget. And that adds up. But if your compiler takes care of much of that, if the compiler points out all the stuff you have forgotten, then you don't have to keep all these things in your head all the time. So dynamic type systems require you to remember a lot of loose ends, but a more strong and static type system gives you an easier job. And this is maybe the background for this fearless refactoring quote. But there is another effect for refactoring as well. Efficiency. Dynamic type systems require you to write more unit tests in order to find bugs. So conversely, Rust might need fewer unit tests. And unit tests are nice. They help you do refactoring in the sense that they catch errors that you introduce. But all your unit tests depend on your code. They depend on the APIs that you test. And when you refactor, you typically change those APIs now and then to make your design better. And that breaks your tests. So unit tests also have a tendency to freeze your design. They make design changes harder. They make them more work. So if you need fewer tests, then you will have less breakage when you refactor. If you have fewer tests, you have fewer tests that break and that you have to go back and fix because the design changed. You know, fewer unit tests, less work in refactoring. So this saves you time. I had a big refactoring I did a while back where I had a major component in a product we were building. And I had to go and put some more features in. And I saw that to put the new features in, I had to make some design changes because putting them in as the design was would make it really ugly. And the design change I had to make was a big one. It was the kind of refactoring that you fear, where you know that when you start out, it will be hours before you can get the code to compile. You usually want to make small changes and test, and small changes and test, but sometimes you have to make a big leap. And this was one of those. I think it took me about 6 hours from I started out until the code even compiled again. And when I ran the tests, there were about 300 of them. Of those 300 tests, 2 had failed. And I looked at those, and looking at it, it turns out that the component would emit some events, and 2 of those had changed order. But looking at the events, the order was not important. Any order was good, actually, between those 2. So the tests were always specified. And when I went and fixed this, they were all green. I had spent 6 hours pulling everything apart, redesigning it, putting it back together again, and when it compiled, everything worked. Nothing was broken. And that was a shock. I'm a decent programmer, but I'm not a genius, and I'd never seen that before. So that there is something here. Yeah, so now we get to the end, actually. We have seen how a strongly typed language helps you detect errors at compile time and help you write correct programs, which brings us back to the title, kind of. I don't think it's primarily about memory safety, or thread safety even. It's about something else. It's about correctness. And what do we mean by correctness? Well, what I think it means, and what the blog article I showed at the beginning means, is that correctness means that if the program compiles, it works as intended. There's a caveat there. As intended still leaves room for bugs. You can have used the wrong specifications, the wrong algorithms, the wrong ideas, the wrong design. It can still fail, but it doesn't surprise you. It doesn't shock you. You know, how could this happen? What's going on here? There is little of that. And that removes a lot of frustration. And using a language which is like that can be incredibly fun and rewarding, and it just feels right, kind of. And I think that is the source of this enthusiasm that we saw with this joke at the beginning. Here's the blog article again, if you would like to read it. So, that's it. Questions? Oh. Yes. Yes. Maybe this works.
Thank you for the talk. And have you found any compiler bugs on production in Rust?
So the question is, have I found any compiler bugs in production in Rust? No. I haven't. Oh, sorry. You mean bugs in the compiler? No, I haven't. But on the other hand, I haven't found any bugs in any other compilers since the 90s either, so not serious ones anyway. Yeah.
Are there any things that you miss from C++ while you write it?
Are there any things I miss in C++ when I use Rust? Yes. I think the standard library is too small. In our line of business, we have to be careful with dependencies. You don't want to use too much third-party code. And I wish the standard library had things like a random generator. It doesn't. I have to use third-party code for that. I'll write it myself. So that could use some improvement. Some people are not afraid of dependencies, and they are perfectly fine with that. But some of us need to be careful with that stuff. So I wish there was more of that. I'm sure there are more things. I cannot come up with them right now. It's not perfect. Yes. All right. If you don't like asking questions in public, you can always ask me later. Okay, thank you.